Mhm. Okay, now we can start. So various algorithms we are going to apply, and on a real data set. And this real data set actually is one of my research scholar, and we collected it from the clinics, and also from the schools, and also online. So forms and all. So this is for patients suffering from dyslexia and all similar dysgraphia, dyslexia. They are poor, I think. So it is with that. Now, what we require, this is just an example, okay? I'll be taking one by one later, but this is just an example to show you, and you can always see how things work. So this gives you an overview of things you can do with this. I'll just copy the thing and explain it because I have already implemented the code. So let us say I'll copy. I'll have to upload rather, not copy. Let's see if I have that data set. Okay, so let's see. It is somewhere here online. Python. It is in data sets, I think 2000 something here. Okay, yes, data 2000. It has 2000 records. Actually, I have trimmed down to 2000 records. Otherwise, the data set was larger. So just taking 2000 records and see if they're okay. You can, I'll just show you how the data is there. So there are these are the parameters actually: ls l1, ls l2 and all, pa phenomenon and all. These are the parameters which we take for deciding whether the person is suffering from dyslexia, dysgraphia, or I've actually shortened it also. So dd and all, I've given a few, changed it so that I don't have to get big names there. So names may have changed, but we can always edit that and minimize to 4 diseases, or 4 ailments, not diseases. Actually, they're it's very unfortunate that some people have this, but anyway. Now, first is pandas as always, NumPy, then matplot, then in sklearn we have model selection, classification report, that is for these actually are for accuracy and all. Okay, these three: classification report, confusion matrix, and accuracy score. This is for calculating the accuracy of the algorithm you are implementing, or the model, or the classifier you are implementing. Now, from here till here, what we have is different machine learning algorithms like logistic regression, decision tree classifier, key neighbors, linear discriminant analysis, Gaussian bias, and SVC. We don't have a random forest here, but we can call random forest also, and may have implemented later. Okay, so these are the actually classifiers. The imports look very big because of all the classifier I've called in one code. I have to call one by one, or I can call once for all. So environment, I've called all of them, and then you have to split. So you have to call this function train test split. The data has to split, and for that also what we have done is we have put a function defined that is split data set. That is the function data set train percentage, feature header, target header. Feature headers we have to pass. In case of machine learning, we have to tell the classes. 1 minute, I'll just show you the data set and show you. This the you have seen, but the last one, that must be the class. Okay, I'll just show you. These headers you have to give these. Okay, in a machine learning algorithm, you have to give the headers, so you have to define them. And the last one is always the class, which is already given that this data belongs to this class. If these are the parameters, then this should be the class. Okay, that is why I always say that machine learning, it's all myth. You're already giving everything. Then what you are trying to do? You're just trying to see that the things are classified. Not when you have already classified the thing, then why you are classifying it again? So that is the thing with the machine learning. But then we have deep learning and transformers, which are more advanced, and I don't have to give all the headers and all. This is supervised learning, and in supervised learning, you have to give the labels, okay, the headers. So we have the supervised and unsupervised learning, which we have already seen. So this is supervised learning. So you have to tell, okay, fine, this is the data and this is what it is. Okay, so we have given that. So what you can do is, if you have a data set, a CSV file, all you have to do is copy the headers, the first row, and put it in the headers in separate, put into double quotes separated by a comma. That's all you have to do. But make sure that your last thing should be the class. The last item should be the class. Okay, it's very simple. Now, headers, we have input path, that is the file data 2000.csv. Data set, we are reading the data, pandas.read data set input path, or I can put the file directly also, doesn't matter, read CSV. X is equal to data set. I use X and Y, so I have put it in X. Otherwise, data set would also do. This has nothing to do with any coding or something. It doesn't matter. Now, I can read it like this, or I can read it like this. Actually, I was checking for the nulls and removing that. That's why I again read it. So you can read it like this also. NA values is nan, and keep default NA is equal to false. That means I'm just clearing out the empty things if they exist. Okay, so I have to see if all the modules are loaded. So I just run it first and see. And okay, let me explain this. This is simple splitting. This is what we always do: train, test, split. And in this, we give data set. 1 minute, I'll just put it in one line. Okay, so we have a data set that is with feature heads, that is these heads, and then data set target headers. Again, it is almost the same target headers we will be passing on, and the train size and the train percentage. This function we will be calling later, and it is going to return your training set, test set, and training and testing set. Okay, so we have the labels and the data, which is divided, and how much we have to divide the percentage we have to decide. So this is the train percentage we'll be passing. 80-20, 30-70, depends. 70-30, sorry, not 70-30, 70. First let me run it and see if things are working fine. It is working fine. There are no empty cells, 0. You can see that. So NA has to be checked. If you don't check NA, then you will have problems running your machine learning algorithm. It doesn't take empty cell. It treats that as a NaN, and then you'll have a problem. It will give errors, and you would not know the reason for the errors. Okay, so excuse me. The good practice is to check your NaN and then proceed. Okay, so I have suffered a lot. That's why I always check. I wrote a code, tested it a number of times, checked everything in the code, changed everything 10 times in the code, and still the errors were coming. Finally, and you don't get Google for that errors. Okay? So you don't get actually the reasons on Google also sometimes. So you have to find out yourself. And finally, I could locate that there was some empty cell in the dataset. Only one empty cell was there, and it was giving me errors because of that. But the interesting part was that the returned error never spoke about that empty cell. So it's difficult to detect. If you're able to find, it's better that you first check your NaN and see if there is any empty cell. Then you can because this is just 2000 records, you can manually do it, or you can simply replace it like we did earlier also. Here we have put the code here, NA values NaN, keep default NA is equal to false. So we'll just not have the NaN values. Okay, so as you can see, there is no NaN or there is no empty cells. There were empty in this also. In this data set also, because this is a real-time data set, so it is quite possible that if you don't get a response from a student or then or the patient, then what happens is you just leave that, and that blank is dangerous for me, for any programmer rather. Okay, anyway, so let's go ahead and see what we can do. This we have read the data, and we have to split, so we'll just call it, and then we'll just see. I'm just copy pasting, okay, because I have already implemented that. So train test split, we have to call the split dataset function. Dataset we are passing that we have already read. I can pass X also and dataset also. That depends on me. 0.7, that is 70%, 70-30. Okay, headers 1 to -1, that is 1 has to be left. Okay, 1 to -1, that is class will be left out. This will be your feature heads. Okay, your data set target heads, these are the target heads, these are all your target heads except for the last one, that is the class. Okay, because that is your that is your target head, this is your feature heads, these are all your feature heads. Data set feature heads, data set target heads, train size. Okay, we have here. Okay, train percentage, feature headers and target headers. So feature headers, these are the feature headers, and target headers is only the class. So -1 gives me the last value of the list. Okay, as we know that if we give 0, that is the first record in the list, and if we give -1, that will be the last record of the list. In our case, our last record is the class or the label. Sometimes we use class, sometimes we use label. Let's print it and see what we get. See, this is the class and rest is the here. Okay, you can print from 0 also, absolutely no issues. We have left first one, there must be some good reasons for leaving that. Anyway, now again I'm just checking another function. I'm just telling you because I had to figure out this thing. For null columns, x dot columns, x dot is null any. If there is any null, then print x null, accessible one, null columns and head. If there is any null, then it will print the data with the headers where it is null. So I had written this code to find out if there is any null in the dataset. Unfortunately, there was none. Okay, so now we have to see the dataset. We always evaluate the dataset before we do anything. So let's have the shape, then display. We'll just display the data and the head. Okay, so last head we can print also. Here you are. So this is the data you have. You can see that dyslexia, dysgraphia, and all, and the data size also you have. Okay, so headers you have printed. Now we have the data. All we have to do now is to implement, but before that we will have print data set. I've used actually stored it into X also, because if I have to use it without changing anything, suppose I change something in dataset, then I won't have the original dataset with me left. So otherwise, I'll have to read it again. So what I'll do is I normally keep it in a variable so that I can use it later. Now I have to describe, get the information about the data, and as we have done earlier also, describe gives you the statistical output, that is mean, standard deviation, minimum, maximum, and your percentage wise distribution of the data, how the data is distributed. So this can help you actually uh, in understanding the data set and planning your algorithm accordingly. So let's have the size of the class also, class wise size. So database dataset dot group by class. That is, you are grouping the data by class. Okay, we have done it earlier also. Group by we have done in the listener. So we have done this. So in this case, class. We are finding out the class. We can find anything, any label. Now classes DD has 209 records, DD2 has 92 and all. So you can see dyscalculia, dyslexia. There's some spelling issue. That's why they are two. Otherwise, it is actually 46, but that's okay. Stammer also, one is small, one is capital. You can always manipulate. You can always correct your data and check it. But for now, it's okay, doesn't matter. Although your calculations may go wrong. DDD 2, 3, 4, 5, 6, 7, 8. Actually, I wanted to give them one name, but somehow they have got all other names, also. MD is there, stammer is different. Anyway, so I have the original dataset with me, which we have not manipulated, so I can always correct it. But that's okay. I can correct here also. I'll have to open it in Excel and then do the corrections. I'll do it later. That's okay. Just have to see. I'll give you the correct one. Okay. So you can run on that. Because these spelling mistakes, the classification for dyscalculia will be different. But that's okay. Just in case this is something different, different diseases, it will be treated as a different disease also. Although dyscalculia is only one. But this stammer is also one. But anyway, it's okay. Just treat it as another ailment. So doesn't matter. Now we have to get the values. So dataset dot values will give you the values. So we'll have array and we'll store it in that. Array is equal to data set. Sorry, data set dot values. So I'll have the data with me 0 to 19 and the last one x and y. We have to get the labels and the data set. So these are the labels we have got, the class in y and rest of the data in x and y. That is the training set and the testing set. This is how to we divide. We'll be dividing it later, but this now just now we have just got that. Now we will be using knn. Let's have knn, k nearest neighbor, and see what happens when I implement knn on this. We have already divided the data. So what we have to do is we have just to we have to call the classifier only. Okay, and then we have to predict. It's very simple. Machine learning, nothing rocket. There is no rocket science in this. Okay, make predictions on validation data set. Well, where has oh the cursor was there. So let's me put it here. I hope I did not do anything. I did not. So on the validation dataset, we have to work on that. So okay, now we have knn, that is k nearest neighbor classifier, which we have already imported here. Where is import? Oh, where has it gone? Here you are. This is the one. K nearest neighbor, knn. Okay, we have called it already, so you don't have to worry about that. Now knn.fit. What we have to do is I'll put it here, compile the model. Okay, so knn, this can be anything. This can be model, this can be key model, or this can be anything. Then knn.fit train x and train y. This we have already split. Okay, I was doing this one data splitting to check manually how we can do it. But train test split has already the data, and I'll show you here. Yeah, this is what is the thing, right? So you can see that. No, we are putting train X and train Y. Okay, and then predictions. For prediction we put test X for predicting the input. That means from your input data set, what you have done from the total data set, you have divided the data into 30 70, 70 30 rather, 70 for the training and 30 for the testing. So training, we are doing train X, train Y. That is, train X is the data, train Y is the label, that is the class. Same now, what I am doing is, this class is the same, so we don't have to worry about the class. Now predictions, kn dot predict test X. Now there could be one question that if data is taken sequentially, then you miss out the 30%, which is the last, and it is possible that there could be a class which is not in the previous 70%, right? But it is not like that. It is actually taken randomly, and almost all the classes are covered. So classes are non-mixed. So randoms, that is why we actually fix the random seed. In this case, we have not, because we are just testing. We're just seeing, okay, what happens if I give a real-time data set. This is a real data set which we collected. Okay. Now, predict is giving the test X. That is the data, not the label. Label is not required right now. Although it has already split. We'll use it later if you want. We can see that down there. Now, kn accuracy. So what we get actually when we classify, we get the class as the output. Okay, so predictions will give me the class of the output. So we have to calculate the accuracy, and how we are going to do that is from here. We are calculating the accuracy score, and we are checking if the classes match or not. That is, the class test Y and predictions are matching or not. The output predictions will give me class, and test Y also has the class, right? Test, we have when we have put this for prediction, this is the classification. That is, your 70% data is classified, and for 30% we are putting the for testing. So 30% data set give me a predicted output of the class, that this particular data belongs to this particular class. We'll see the output and we'll see, and then we are checking whether they match or not. So let's see if they really match. Okay, so kn accuracy is 94.84%. That is very good. And now this is the confusion matrix which we have created. This is how the classes are distributed along the diagonal. Now the data which is outside the diagonal is not actually classified properly. If everything falls in the diagonal, major diagonal, then it is 100% accurate, because this is not 100%, this is 94.84. So some data has to be scattered around somewhere. In this case, you can clearly see that it is scattered, and this is why you can see that it is not 100% accurate. And 100% accuracy is actually not good also. It's okay. Anything above 60% is fair enough. And anything above in 90s is very good. This is a very good output. So we have properly classified, and this may be because of the reasons that the data is not properly done. So we have to manage the data set also. Okay, now this one you can see for precision, recall, F1 score, and support. This actually gives me further statistical output, which tells me mathematical output, not statistical. That gives me the how uh, the accuracy works. So you can see the down there accuracy. You can see 0.95 and the 601. That is the classification F1 score. Support vector is the total number of data which was passed to it. macro average and the weighted average. They all have mathematical formulations, and I can share it with you also. The precision and recall, we have false positive, false negative, true positive, and true negative. And these are on these four parameters, we calculate precision, recall, F1 score, and support. Right? So false positive, that means it is showing that it is matched, but it is not actually matched. It is not correctly matched. Matching is there, but it is not correct. That is false positive. False negative, that means it is a match, but it has shown that it is not a match. Okay, so that is false negative. False positive is, again, it is showing that it is good match, but it is not. And true negative is, okay, so whatever you have given is negative, is a negative in this case also. So if it is not matching, it is not matching. So true negative is okay, it's fine. Other is true positive, false positive, true negative, and false negative. True positive again correctly matched, true negative is correctly matched, but in negative, but it is matching is correct. False positive and false negatives are the ones which cause some issues with the precision. Okay, otherwise the classification is correct in both the cases. I'll show you the formula later, how it is calculated. You can normally when we code, we use the formulas to calculate. So inbuilt formulas are there. We can use the inbuilt formula also, but normally we use the calculations for our papers, for our research papers, and here also. 1 minute. Okay. So you can see that Canon we have implement others also. We've already called others, so we can do that also. We can use another method. I'll show you. Simon we have. I'm not sure it is inbuilt, but let me see. Okay, so what we are doing is import Simon as SNS, confusion matrix shape, and here labels are the classes. Okay, we are calling heat map. I'll just show you. If Simon is inbuilt, then I won't have any issues, but this will give you a better output, beautiful output like this. You can see the classes, how the classes are there, and how the data is distributed. You can see that. Okay, so from this heat map, you can see that how accurately the data is there. So if you want a better output, so what you have to do is you have to call cbon, otherwise everything is from sklearn. Then you have to again calculate the confusion matrix which was already there, but just for displaying we are using cbon. So you can use cbon also to plot your confusion matrix. You have an option, you can do that if you want. So let's have the prediction, how the prediction came, and see whether they are correct or not. For this, I'll have to use a loop. I'll just print the features and the predictions which we have got. Predictions we got here. Here, we got the predictions. So I'm finding the length till length. We have to go 0 to length. Features, that is list xi, and predictions. This it is predicted properly or not. That is what we are doing. So features, this is the feature class dyslexia. This graph here, I can do that. I can print the feature. I can even print the class which was the default class. So you have an option, you can see that it is properly matched or not. You can print the label also along with it, so that you can actually understand that the matching is correct or not. But we have already done that. So this is another way of doing things. And now we have logistic regression. So we can do a logistic regression now. They all are same. Implementation is same. All you have to do is change the algorithm. So no rocket science in machine learning. AI is a myth, as I always say. So model, we have to call the model, then data set. You can use different ways of doing that. Okay. There may be some cut-offs, okay. So logistic regression we have called. X train, Y train, I've just used the capitals, that's all. LR.fit, this is compile the model. I've just stored it as it X train and Y train because it was train X, train Y, this is what we got. But I wanted like this, so I just put it here. So X validation, this is X validation, that is test. This is train, okay, compile, X train, Y train, and X validation. Then accuracy score is a Y validation, that is label only basically. And predictions we have put in and found what the classifier is talking about. Let's see, there could be some error because, okay, that's fine. In this case, I printed everything. Okay, so here the accuracy score has dropped to 83. So LR doesn't give a very good accuracy, and you can see from the confusion matrix that the data is distributed here also. It is split over. So it is not in the diagonal. This is missing somewhere. And this is precision recall and all. Now, see, dysgraphia matching, DD matching, dysgraphia matching. What is not matching? Here, you can see this. This is not a match. So what is there in the original data set and what is the output is on the right hand side. So DD4 does not match with dyslexia. Okay, here also you can see DD6 is okay, dyslexia is okay. So this the DD2, this one is not matching. You can see that. So you can see from here that what is not matching. Okay, so you can work on the data and then you can get a better idea and you can get better results. So you have to normalize your data in such a way that you get a proper result. But that's okay. It's not necessary that you get very good accuracy with all the algorithms. Algorithms differ, and so does the output. So let's see, and we have LDA, and let's see if LDA gives me better accuracy or I have the same almost similar thing. I have to copy here. So extreme writing I have already copied because I was using extreme writing, so I have already done that. So I just have to use the same code and print it. So LDA, linear discriminant analysis you are calling, then you just compile the model. Compile, then predict, same, nothing different. Only this is 82% not good, not better than this also. Canon was giving better results, but this is not giving me any good results, so that's okay, doesn't matter, not necessary. So we can try with some other algorithm. So LDA is not giving very good results. Let's see what other algorithm can give me a better result. I can always print and see what is there. We can have decision tree classifier, have this also, and again we have to just call and rest is same. Only we have to change the classifier, compiling the same. I've used different names. Okay, normally people use a model and do everything, but then it overwrites. I don't want that. I want to keep the classifiers as it is. So CT is going to decision declassifier. You're calling the model, then fit, then predict. Same as before. You can find this is has given good result. This is 97%. That's not bad, and you can see that the scattering of the data is just around here, so it's not bad. You can see that also. You can see the matching if you want. You can print your. You can use the if thing and check if you want, and you can use Seaborn also to print the confusion matrix. I will put it here only. I can put it here. The earlier one I did not, but in this case you can. And you can see what is not matching and why it is not 100% accurate. So you can do that also. But it's okay. 97% is a good thing. Then we have Gaussian NB, which is one of the most famous algorithm and was the favorite of most of the coders for a few years. But I never found this to be very accurate, and I never found the results to be very encouraging. I never found it in any of the data set, even the real data set or in some of the benchmark data sets. It has shown good results, but otherwise I have not never found it very interesting. But it was the favorite at one time. So again, call the classifier, then fit and predict, and then we have the rest. Accuracy and all is the same. You see, this is 62%. As I told you, that it doesn't give very good results, so they are not very encouraging. But that's okay. It may be because of the data set we have. So all the algorithms, because they are all mathematical formulations, they may not be working the same way. There could be some changes. That is part of it. And another one which was favorite and which was the favorite of all the professors, I can see that state vector machine. Just put it here, SVM. One of the most favorite and which was forced on by the professors and all, that you should be using this. But again, I never found it very interesting. So we call it SVC. SV is equal to SVC, then fit, and this is again compile. You can run, but it can give good results sometimes, but you can see that it is just giving 33.11%, which is very, very bad, and you can see that how the data is distributed. So it's not able to classify properly. The data set is very small. So there's no point in having such algorithms working. But there was one time when everyone was insisting on using SVM, as it was easy to implement, and we had very tools to implement them. So it was insisted, but it's okay. If you don't find it interesting, then don't use it. You just have to run all of them, all the algorithms you can run and see. I think we have covered, yes, we have covered all. We have done logistic regression, DCT, decision tree classifier, KNN, linear LDA we have done, Gaussian NB we have done, as SVC we have done. The ones which are listed here we have done. Although we have a few more, like we have random forest, which was again one of the favorite everyone, even mine also. At one point of time, it was in machine learning, it was the favorite. But again, it is not necessary that it even that will give you good results. It all depends on your data. So you can see that everything is called the same way and done the same way. There's hardly any change, right? As far as implementation is concerned, you can see that you're calling the, and I'll show you one. This is not the one. Okay. So you just have to call the classifier, then fit and predict. Rest is just the calculation. Just 3 lines of code and the machine learning is implemented. Okay. So machine learning is not a rocket science to implement because everything is inbuilt. It is already there given to you. There was a time when we had to adjust the weights. We have to give everything manually. We had to manipulate manually. Things we had to do, like for prosthetic leg, we designed my for one of my student in IIT. He went to IIT and they, if you can find him, he's there for the first person in India to do the prosthetic legs. He was in the exhibition also long time back. So he has done his PhD now from IIT Delhi. For him, we worked on a neural network, and we had to actually manipulate manually and code. The source code had to be changed, although we were using MATLAB that time. But still, it is open source. You can always use the code and change it according to your requirements. So it had to be changed because you have to see the algorithm how the leg moves. In a prosthetic leg, it is very important to see how your one of the leg moves. Like if it is for the left leg, then you have to see how the right leg moves and how the left moves with the right. So that synchronization is very important. And he was my student who was able to do it perfectly. His professor was in Delhi, so they both worked on it. My only contribution was to help him understand MATLAB and the algorithm, how we can manipulate the algorithm, how we can change the algorithm, and implement. But the rest, the hardware part, that is the hardware part is important. How the hardware was designed, it was designed in IIT Delhi, and then the algorithm was ported, and obviously some changes they would have done, although because in a software what we can get is we can just plot and see whether the graphs are okay or not, like we have seen here also. I can say that it is 100% accurate or 97% accurate, but when I implement the hardware, it may be different, right? So hardware depends, and in robotics, yes, it may differ because the data we are getting, it all depends on that. How many spikes, what spikes we get, what noise we get with the data. We have to clean it. We have to normalize the data set, and then only we can implement your machine learning algorithms properly on that. But even if the accuracy is 60%, more than 60%, then we can say, okay, fine, it can work. Less than this, like we have seen 33%, it won't work at all. You know that. You don't no point in trying it also. But since deep learning and transformers have come, it is always better to use the latest techniques, latest technology, because obsoletes won't work, and with the hardware also, they won't be supporting much of that. So anyway, whatever data you get, you can actually try with the hardware because you're from the machine side. So you should be implementing using some hardware, and you can start off even IoT devices you can design with intelligent IoT devices. You can use Arduino or TI. I normally use I prefer TI boards, Texas Instruments. So I prefer TI, but on the cheaper side we have Arduino, which is easy to implement. Even TI is easy to implement. So we have IoT TI boards also, and Arduinos also. So whatever you get, just if you have in the labs, then it's good. If you have not, you don't have in the labs, then you can always buy them. This is a simple 400, 500 rupee board. Even TI board is was around 1000 when I last checked. So it is not very costly as long as you are using it for you are making a good use of it. But if you're not, then there's some point in buying it also, right? In ITs and all, it is very good because these TI guys just give them free of cost. Everything is free of cost. 1,000 boards, 100 boards, 200 boards, they just give free of cost. So it's very easy for those guys, but not everywhere. So, but if you want to do something, then you have to implement actually and see how things work. And as I was told that there was some robotics issue, where you have to implement machine learning, then I can tell you one thing. In 2008, I think, yeah, in 2008, I helped my students design a robot and which defeated IT Delhi. They got number one position, and they were selected for Singapore competition. But unfortunately, they could not get the sponsorship to go to Singapore and fight on the international level. The design was good, everything was good, but there was no funding, so they had to withdraw, and it was costly for the students actually to go there and compete, because staying there was costly. They could travel, but staying, fooding, lodging, everything is costly. Although they had some offers from the college universities outside, but still it was costly, so they could not go, and the college did not sponsor. So that was a bad luck, but they competed and defeated IT Delhi. That was their achievement, and I had my role in that, in designing it. There was no AI involved as such. A little bit, not much. They were all from electronics, so they could understand. But that's okay. You can always understand electronics. It's not a big deal, right? And we designed a drone also in 2007, 8, 7 and 8. Yeah, that was the first drone we designed in 2007. That was when there were no drones actually, and it was not going up. So my students used helium that time, but I told them that the propeller has to be properly done. You could, you will have to use four propellers. This is what they did later. But anyway, that was long time back. And now things have changed over the years, and you could have seen on meeting day that how beautifully IT Delhi people displayed the drone power of India. So from 2007 to 2022, it has gone a long way. But it's okay, good. Things should happen. Anyway, so now what we have to do is we have the assignment given. So you have the assignment with you. You have to go through it, and please don't try to copy. Okay. I can check the flag also, but I won't be doing